Thank you. Hi, everybody. I'm Tarek Kurd. I'm the Chief Architect of CodeSIP. I'm based in Bristol in the UK. I'm not a Cherry researcher. I'm a processor architect, and my role in all of this is going from the excellent research that Cambridge University have done and turning that into a real product and something that's RISC-V compatible and which we can standardize. Now, I turned this presentation into a poster, which I presented on Tuesday, and we've had a Cherry poster each day with my two colleagues who are actually sitting in the middle there and put their hands up if they like. And also, we've got 8 members of the Cherry team, including 2 who've been on it since the very beginning in 2010. So I think it's safe to say that anything you want to know about Cherry, the person who knows the answer is somewhere, ideally in this room listening to me, but definitely in this building at this time. So because I've had so many questions about what is Cherry, how does it work, how does it fit together, I'm hijacking my own presentation, and I'm going to do it as basically a Cherry FAQ for a few minutes, and any time that's left, I'll run through the slides. So I shall go to the slightly marketing type slide first, pointing out that Cherry will prevent things such as heartbleed. Heartbleed is obviously something we're all very familiar with. But I'd like to say a few other things. So Cherry avoids a whole range of modern exploits. It's primarily about memory safety, but it also includes control flow integrity. It exploits buffer overruns comprehensively. It prevents return-oriented programming, jump-oriented programming as well. So it adds secure compartmentalization or sandboxing of software, and it works with, but it makes redundant things like stack protect, shadow stacks, landing pads, all of these things, address space, layout, randomization. No problem with implementing all of those things on a Cherry system, but you can save your memory and your runtime by taking them out. That's what we're claiming. I've been told that a large software system such as Android will spend a significant amount of time on compartment switching up to 80%, and we believe that when Cherry is correctly used, and this may involve updating our specification, and we don't have a problem with that, then we expect that overhead to go down significantly, and so the system will run much faster. So we're trying to present Cherry as an optimization as opposed to a cost in the system, because other mitigations are expensive. So the main objective is to make your software memory safe. So C and C++, we all know, are unsafe. Your pointers can point anywhere. You're protected by your PMP and your page tables, but they only give very coarse-grained protection. Cherry gives much finer protection. So then people say, well, what about Rust? I can just use Rust, and then everything's fine. Well, actually, it's not. And if you want to know more about that, actually, if Carl puts his hand up, he will tell you very much so about why that's not the case, but I'll just give you a couple of sentences. The first thing is that the Rust compiler will only detect what it can detect statically. Cherry is fully dynamic and will check everything at runtime, no matter what's happening. And the other thing is not all Rust code can be safe anyway. So unsafe Rust code is completely unchecked. So what we find is actually that Rust and Cherry are compatible and very good together, and we promote them being used. And in fact, the Cherry Alliance, which will be announced properly at the next summit, has a working group on porting the Rust compiler to Cherry. So it's definitely a good thing. Rust is a good thing. It doesn't make Cherry redundant. Something else I'd like to say, so compatibility mode. So Cherry cores, if you choose to implement this particular part, will allow you to run 100% of your existing RISC-V code. And on a sensible microarchitecture, there'll be no slowdown. It'll be doing exactly what it did before. So it is a choice in the M-mode software to then start enabling Cherry. And so you can run your software with your stack protector and your shadow stacks and all of this, and it's absolutely fine. You can put your Cherry core in, it will still work. And then at some point, it gives you an upgrade path to gradually enabling the features. One particular very useful mode is we call it a hybrid mode, where you can have a Cherry system where you've recompiled your code, so you've got fine-grained memory compartmentalization, or fine-grained checking, but you can call existing code that hasn't been recompiled, so any existing RISC-V code, typically a library function, and you set up the instruction fetch range and the memory range that code can access, and then it runs within that compartment perfectly. It cannot access anything outside. It can corrupt its own internal state as much as it likes, but it can't do anything outside, and then you jump back to the kernel. That's known as the hybrid kernel. Okay, next slide, at last. Right. Okay, so this was sort of based on a very simple marketing slide. The point is, what we're trying to say is that every register in the RISC-V core becomes double the width and has a hardware-managed tag bit. So double XLEN, which we call CLEN, we call it a capability. Capabilities have been around, I think, since the 1960s. There are people in this room who know the history much better than me. So the idea is you have your address field exactly where you expect it to be in the least significant half. In the upper half, you have bounds, so base and the top bound, and all accesses must be within those bounds, and you also have encoded permissions. There is a joint encoding between the two halves, so you cannot just take the bounds and encoding from one address and just apply it to another and expect it to work. So you have to consider the whole capability as an atomic type and update it correctly in one go. So what happens is, so the software can access memory based on all the capabilities in the register file, and obviously, if you have the correct permissions, you can use those capabilities to then go and load more capabilities from memory, and then obviously you can access memory using those capabilities. And at runtime, what happens is every time you do a load or restore, you're checking every single byte that you access against the bounds. You're also checking that you have the permissions. And this should not add anything to the execution time of your core, providing it's a sensible microarchitecture. So we don't see any overheads there. The bounds encoding is done in a floating point style. So you have an exponent and a mantissa. So if you just allocated a few bytes, you can do it to the byte, absolutely arbitrarily to the byte. And then as the range increases, then the exponent increases, and obviously the mantissa shifts up, just like in floating points. So you can go up to multi-gigabytes, and then eventually the whole address space with a single capability, which is the reset state. The reset state covers all of memory. The other thing we say is that Cherry renders the PMP redundant because it offers much better memory protection, again, down to byte granularity. The PMP is expensive in terms of power and area because it's doing a very complex, probably 16-way lookup where you're comparing all the ranges against every other range. And Cherry, you just have this specific capability and you just check against it. Like, for example, if you're running code on the stack, which is quite common, the stack pointer, you've already got the bounds permissions, you're just repeatedly checking against the same bounds and permissions. So what we found is that by removing the PMP and then adding Cherry into the core, then you end up with more or less the same core area, possibly a bit smaller. Cherry does come with a hardware-managed tag bit, though. So the hardware-managed tag bit is saying whether a capability has been created according to the correct rules, and so can be used for memory dereferencing. This bit does also need to exist in the memory, so every 128 bits for RV64, you will have one tag bit in your caches, and some of your system memory will need to be capability aware and support tags. You don't need to do it for the entire address map, unlike MTE, which uses 4 times as many bits and does have to cover the whole address map. With Cherry, it can be selective and uses quarter as many bits and is absolutely deterministic, whereas MTE is statistical. And, and so Cherry is a hardware and software co-design. So when you have a capability, then the software can create other capabilities from it, but all it can do is reduce reduce the bounds or reduce the permissions. It can't do anything else, really. So the OS will create a task, it will give it capability saying, you can cover this memory range, and then the software can then reduce that and then pass that on to the next piece of software. And then that next piece of software can only access what it's been given permission to, and it cannot access anything else at all. So there's the part which is the hardware checking, and there's also the provisioning of capabilities in the OS. So the two things have to go together. And we also have some slightly wacky ideas, which I thought I'd mention, to do with an optimized mem copy, if John's in the room somewhere, I'm sure he is, where you can give it a capability because you have an address and you have bounds. You can say, mem copy some bytes, and then it will update the address and give it back, and then the mem copy will keep going until you hit the top bound. So there's an idea. Right, I should now do the presentation very quickly. How long have I got? 3 minutes. Oh, OK. Right. I would like to mention the fact that it is multi-architecture. So certainly for the Linux porting work that's going on, there is code sharing between ARM, for example. It was originally MIPS. Now we're obviously based on RISC-V, because that's where we are. And there's also Cherry IoT, which SCI are developing, which was originally from Microsoft, which is a very nice solution for IoT-class devices. And what we're trying to do in the Cherry TG, and also in my work at Codasip, is we're trying to have a single Cherry spec that covers the entire range, all the way from the tiniest devices up to servers. I will just say that we did a demo, it's Carl again, and Troy, who's at DAC this week, because both events were at the same time. We did a demo of our A730 Cherry Core at the summit last time, and we hope to have a significantly more comprehensive demo at the summit coming up, I think in October. What else? We've got our spec on GitHub. It went on there in January. We're up to version 0.8.2. We're just making tiny incremental changes at the moment as we find things that need fixing. We spent a considerable amount of time optimizing and refining what was in the original Cambridge Cherry spec, the Cherry V9, and basically making it really RISC-V compatible, making it fit really well, and I don't have any time to talk about those. Lots of changes. Very quick list of extensions. The idea is the top line is the pure cat machine, so you can have a Cherry machine which requires everything to be recompiled. The second line is the hybrid, where you can also run existing code in a secure sandbox. And we have a whole lot of other things that we're looking at as well. The blue ones, we've often got pull requests, but they need more work. The green 3 at the top are stable. So we've got RVA22, all the mandatory extensions fully covered. We've got that implemented. We're very happy with that. We're moving to RVA23, which means we have to get Vector and Cherry working, which essentially is simple. Every unmasked byte of every load and store is checked against the bounds. But we'd also, another mem copy idea is to use optimized mem copy through vector registers, which would mean storing tags in vector registers, but that would be in the future. Vector and hypervisor, something we've talked about a bit in the past. We talked about this week with Krista, who's sitting there, about how we'd like to have a hypervisor with different OSs running, different guest OSs, and some of them will have Cherry, some of them without, and we'll make that happen. So we'll virtualize where the Cherry is enabled. Pointer masking I've looked at. I think it's just an address range, which you get Cherry to ignore. I think it's fine. Because I ratified all the code size, obviously I've done all the code size extensions, so they're all compatible in capability mode. Yeah, so 100% compatible RVA22, working on RVA23, and there's an upgrade path because you can run all your existing code. We're working on Cherry IoT compatibility, and world domination is always the goal. I think that's it. Wow, that was quite tiring. That's it. Thank you.
So I guess we've got time for one quick question.
OK. So there's something I didn't answer in my FAQ at the start.
Thanks for the talk. Since x86 is like completely proprietary and closed, how did you manage to do a prototype of Cherry on x86?
I know nothing about the x86 version, but the people who do are in this room. So I can't. Oh, over there. Look behind you, over your left shoulder. Ask them afterwards. They'll tell you everything, I'm sure.
OK.
I've only worked on the RISC-V version.
OK. Thank you.
OK, thanks.